This is CM3900 exercise question 2 in the document vector 2, and I've just written out the answers here, and I'll just give a bit of description of the main points to pick up on. Well, in part A we're given f of x, y, z. Now if we see x, y, z, we should immediately conclude we've got spherical field, and that is given as x squared plus y squared plus z squared to the power 3 upon 2. And the thing to note there is that that can be rewritten as x squared plus y squared plus z squared to the power half, which is by definition the small r will not be the radial distance from the centre of the sphere to the surface of the sphere. A bit like using Pythagoras to get the length of the hypotenuse, which would be the square root of x squared plus y squared. It's just the extension to the third dimension. Now, the first thing we're asked for is to find del f, and we should refer to equation 2.1 for this, which tells us that del f is equal to f dashed of r times r hat. Now, our f of r here is r cubed, because we've got x squared plus y squared plus z squared to the power half to the power 3, because the power 3 upon 2 can be rewritten as a half times 3, and therefore we have r cubed. Now, but to get del f we need f dashed of r, so the derivative of r cubed, which is at 3r squared, and del f is given by that derivative times r hat, so that's del f, 3r squared r hat. Secondly, we're asked for del dot f, for which we should refer to equation 2.2. It's given as 1 upon r squared times, in brackets, r squared f dashed, in other words the derivative of that with respect to small r. So if we follow through in the next line, we therefore see that del dot f, I've just put in there because we need that for finding del squared f, which is what we've been asked for. That by definition is del dot del f, which I've noted up here. That comes from equation 1.18 in vector 1. So del squared f is given by del dot del f. Now we know that del dot f is given by 1 upon r squared times the derivative of r squared f. Therefore, del dot del f is 1 upon r squared times the derivative with respect to r of del f, and we already have that del f is 3r squared r hat, and that has to be multiplied by r squared, hence the appearance of r squared in there. And if we follow this through, we have 1 upon r squared times the derivative with respect to r of 3r to the power 4, because r squared times 3r squared is 3r to the power 4. Derivative of that with respect to r is 3 times 4r cubed, which is 12r cubed, and then 12r cubed divided by r squared is just 12r times r hat. That's the final part there. Now in part B, we see that we only have x and y, so we should note that we have cylindrical fields, and by definition, square root of x squared plus y squared is large R, or capital R, and so we can rewrite this expression g as sine alpha r divided by r times the vector r, where the vector r is defined as xi plus y j. Furthermore, we can simplify this by saying that the vector r divided by r is the unit vector r hat, capital R hat, and then we can move on to the question. What is being asked for? We're asked to find del dot g and a scalar small g for which large G equals del G. And we can use equation 2.5, which tells us that del dot G is given by 1 upon capital R times, in brackets, Rg dash, so the derivative of Rg with respect to R. So that gives us 1 upon R times d by dr of R times G. Now G is replaced with its definition of sine alpha R times R hat. Now because we've got two functions of R, we've got R times sine of alpha R times R hat, we need to use the product rule to get that derivative. So the next line is 1 upon R times, the product rule, remember, says derivative of the first function, so the derivative of R, which is 1 times the second, which is sine alpha R hat, plus the derivative of the second, which will be alpha cos alpha R hat, times the first, so times R, hence the alpha R in there. And then the last part, small g, is simply the integral of capital G with respect to, that should be capital R, and G is sine alpha R hat. The integral of that with respect to capital R is minus 1 upon R cos alpha R.